Today, I'd like to talk a little bit about cloud seeding and about some innovative methods and techniques that we're thinking about in this. Anyway, cloud seeding, is it a solution for droughts? So we're seeing droughts nowadays. People in France are very worried about there being a lack of water. And of course, desertification is a major issue in the Middle East, in North Africa, and in other regions of the world. And people are doing cloud seeding. There's a lot of programs that are being conducted or have started. Saudi Arabia, your country, is now starting to look at the cloud seedings. There's a big program in cloud seeding at the United Arab Emirates, but it goes on in China, in Europe as well, and in North America. And so is this a solution to the lack of rainfall due to climate change? And I was just reading yesterday that in Canada, an area has burned with wildfires that is equivalent to a quarter of the area of France. And this is mainly because of the lack of rain, which is making the forests very dry. So the question is, can cloud seeding be a solution to these problems? And basically, let me just run over very quickly what is the basic concept of cloud seeding. The idea is to stimulate water droplet formation in clouds in order to enhance precipitation. And to do that, you seed the clouds in some way by sprinkling materials. So past it was silver iodide was the first material to be chosen, which has a crystalline structure similar to ice. People have used dry ice. And more recently, in fact, people have turned to what they call hygroscopic salts, salts that are going to absorb water. And the typical things that are used are sodium chloride, potassium chloride, calcium chloride. And these can be disseminated into clouds in a number of ways. For example, the United Arab Emirates and others use aircraft. Some people have tried rockets. Some people use ground-based guns to shoot into clouds. And something that's become very popular is the use of flares, pyrotechnic flares that are airborne typically by aircraft. But when we were preparing a proposal for the United Arab Emirates, I became aware of a company in France called Celeris, which actually uses balloons to carry these pyrotechnic flares into the clouds. And I'll talk a little bit about their work later on, although I must say that if you really want to know a lot more about what Celeris does, you should really contact them and they can give you a full details about their program. One of the things, though, if you're going to do cloud seeding, you have to have a cloud. And that's a very, very interesting question scientifically, because the question is, how are clouds formed? And in fact, if you look at the basic science of the production of clouds and subsequently precipitation, you find yourself in a question that is a really fundamental question in physics and chemistry. And that is the change of phase from a gas into a liquid, and from a liquid into a solid, or for a gas directly into a solid. And in this case, we're talking about water vapor, that its origin is mostly from the sea. And you've got a vapor that you would like to convert into rain in the form of a liquid. Sometimes you may want to convert that into snow if you happen to be in an area where there's skiing activities. But very often you actually want to avoid producing solid materials such as hail or ice. But this phase change is really something that's very fundamental, as I say. As I mentioned, I work in combustion, and in combustion, gases are converted into soot particles, and we really don't know how that occurs. In fact, there are models for it, but none of the models are complete. And so basically, in order to change a gas into a liquid in the form of cloud, you need something called the cloud condensation nuclei. So you've got a water molecule, and you want to create something that's equivalent to a nanoparticle, and you want that nanoparticle to grow into a droplet in such a way that that droplet will fall out of the cloud in the form of rain. And so it involves a process that in chemistry and physics we call clustering. So molecules are clustered together to form multimolecular systems, and ultimately you want those to grow from the molecular angstroms scale into the nanometer scale, so to form nanoparticles, which then will go on to aggregate with more. They'll cluster with more water molecules to eventually form the droplet. And it's very interesting because in fact, how do you form these cloud condensation nuclei? Well, in fact, for many years, it's been known that one of the actors in this field is actually sulfuric acid, which is rather surprising. And sulfuric acid is something that comes out of industry. We talk about acid rain, but also it's produced by volcanic action. So volcanoes can spew sulfur dioxide into the atmosphere. And that is actually one of the major mechanisms for producing clouds, because of reactions involving sulfuric acid molecules. We'll see in a minute that there are other species that appear. One is called pinnenes, which are large oxygenated hydrocarbon molecules. We call them LVOCs, which is extra low volatile organic carbons. And these are emitted by trees and forests. And in fact, in the photograph here is a picture I took in from the balcony of our apartment in my parents-in-law's apartment in Romania, overlooking a forest. And you can see the clouds arising out of the forest. Another actor is actually ammonia, and that is produced by agriculture. And ammonia is emitted by plants, and it finds its way up into the cloud region where you would normally form clouds. And it's acted upon by sunlight, and there's a whole chemistry that goes on there to produce materials that activate cloud condensation nuclei formation. Other source of aerosols is the sea, and in the coastal region you have very high concentrations of nanoparticles. In fact, I remember seeing a talk where they showed the concentration of nanoparticles on the coast of France, and it was much higher than you ever get in the middle of Paris during a pollution event. Emergency. And so these are sources of cloud condensation nuclei forming materials that can lead to rain. But how I actually got interested in all of this was because I read about an experiment that was done at the High Energy Physics Laboratory of CERN in Geneva, Switzerland. And they produced an experiment which has got the odd name of CLOUD. And the idea is it's a cloud chamber, a bit like the Wilson cloud chambers that were used in the early days of atomic and nuclear physics, where an ionized particle generates the formation of droplets that can be visible. And this is a technique that was used widespreadly in nuclear physics. But they built this apparatus because they wanted to ask a question that people had asked, and that was a question: do cosmic rays affect rainfall? And cosmic rays are ionized particles, high energy particles that arrive on Earth. Normally, they're deviated by the Earth's magnetic field so that we don't get them on the ground, but they're absorbed in the atmosphere. And the question is, do ions enhance rainfall? And really the question was asked because rainfall can often, climate is something, not so much climate, but the weather is something that's very changeable. And it's very much affected by solar cycles, and cosmic rays in themselves, or rays, the solar wind, for example, that is affected by solar cycles as well. So this experiment is a big tank that's filled with air, with different levels of humidity, and they fire high energy ions from a proton accelerator into this chamber, and they look to see what the effect of the ionization is and what are the effects of the different parameters in the chamber. And they can add the different materials they can seed the chamber with different materials to see how they have an effect on this cloud formation. And the findings of their experiments are extremely interesting. And I mentioned they find that these pinene, these extra low volatile organic compounds, are great catalysts for forming cloud condensation nuclei, but also something that was rather perhaps surprising, and that was that an amine compound called dimethylamine, with the formula 2-methyl groups attached to an amine NH group, even in parts per trillion concentrations, would enhance the formation of cloud condensation nuclei by up to 4 orders of magnitude. In fact, it's a super catalyst, and this was published in Nature magazine back in 2013. I happened to have a subscription to Nature at that time, and I read about this, and I thought, this is very exciting, that dimethylamine and ions. They were looking at ions, and ions have been something that I've been interested in throughout my whole career, working with plasma physics, atomic molecular physics, as Suleiman had said. And just about that time, Suleiman Al-Shamari, who's now Dr. Suleiman Al-Shamari, was my graduate student in Rennes. And I gave him the project of looking at the ion chemistry of dimethylamine, and in particular to look how dimethylamine ions would recombine with electrons, and something called dissociative recombination. That's one of my specialities. And this was something that hadn't been investigated before, so it seemed to be an interesting project, and it had a link to cloud formation and of course, climate change, which is something on everybody's mind these days. If they're not thinking about artificial intelligence, they're talking about climate change. And the result of that was a paper that we recently published, looking at electron collisions with dimethylamine and trimethylamine molecules and molecular ions. But the thing that was very, very interesting with that, when we looked at trimethylamine with 3 methyl groups attached to a nitrogen atom, and you looked at the ion, it had an ion recombination rate, the rate of capture of electrons, which was very typical of other species, other rather complex molecular ions. Dissociative recombination actually doesn't vary very much from one ion to another. But when we looked at dimethylamine, we got result that was 50 times higher. And this was not normal. We couldn't believe this measurement. But actually what we realized was that when we injected dimethylamine molecules into our apparatus where we had generated electrons, in fact, these molecules were capturing electrons and making it look as if the ion was capturing electrons. In fact, it was the molecules that are capturing electrons. And that's a process called dissociative electron attachment. And it is a process that varies very, very widely from one molecule to another. And whereas dimethylamine is really quite efficient for capturing electrons, trimethylamine doesn't capture electrons at all. So in fact, dimethylamine is actually quite a unique actor in this chemistry, in this range. And so knowing that dimethylamine was a very efficient catalyst in cloud formation, and that it would capture electrons to form negative ions, well, I asked myself, well, if you've got a negative ion, now you've got a nice stable charge there, and that charge can attract other species. It can attract positive ions, for example. Negatives attract positives, but it also attracts polar molecules. And one of the things, though, at the time, the apparatus that we had was designed to look at electron-ion recombination, not necessarily electron attachment. And although we could see that we sort of formed negative ions, we weren't really able to make definitive statements about what negative ions were being formed. And so that's one of the things that we would really like to do in the future, is to look at the negative ion chemistry involved in that. It's my belief that, in fact, that when you attach an electron to a dimethylamine molecule, a DMA molecule, that it actually attracts other DMA molecules to form clusters. We actually saw clusters formed, positive clusters formed in the apparatus. But I think these are probably the actors that are going on, and they will attract other molecules in the atmosphere when that occurs. So at this stage, we could see that DMA attaches electrons, it captures electrons, that enters into an ion chemistry. And I have to say that ion chemistry is orders of magnitude faster than neutral chemistry, the sort of chemistry that you do and you learn about in high school chemistry or even university chemistry. But ion chemistry is very, very rapid because of this ability to use the electric field generated by the molecular ion to capture other molecules that are polar, and one of the most polar molecules we know is water. That water is an absolutely fabulous substance because it's so polar, because it forms droplets, it forms ice, and it really is a very remarkable substance that we've been given on Earth. So anyway, getting back to cloud condensation nuclei, basically there are two mechanisms that you can think about. You can think about neutral water molecules bumping into each other, colliding with each other, clustering with each other, eventually forming something bigger and bigger, and eventually forming a droplet. That's called cluster collisions. But there's the other route, and that is the one that if you get put a charge under one of these molecules, then they form cluster ions, and these cluster ions get bigger and bigger and bigger, and there's a much faster reaction rate due to the attractive nature of the electrostatic charge. Okay, so that's let's say we know that dimethylamine is a very active catalyst. We know that it can be you can make a negative ion out of dimethylamine. When dimethylamine was identified in the cloud experiment as a major player in this process, people started to look at why it would act so, and they interpreted that in terms of the stabilization of clusters. When the dimethylamine collides with sulfuric acid, let's say, then you would stabilize the clusters and allow them to grow. But it's my belief that, it has been my belief that in fact the negative ion nature of dimethylamine or its daughter products is one of the major factors involved with nanoparticle formation and subsequently CCN formation. However, having said that, you need to have a source of electrons. And in the upper atmosphere, in fact, there are very few electrons. So that's one of the reasons that people have argued against ion formation as a form, as opposed to neutral formation. There just aren't very many ions there. However, if you put dimethylamine into a situation where there are a lot of ions, then let's see what happens. And in fact, we did an experiment at the University of Orleans in France, where we injected dimethylamine into a plasma apparatus, one of the typical sorts of apparatus that's used for making semiconductors. And in that apparatus, there was an argon plasma, an argon ionized gas. So there were lots of electrons around. And when we injected DMA, we immediately got dust particles formed. And the thing is that these plasma apparatuses, they have a potential well that is a positive potential. So if you can form negative ions through collisions, these ions are trapped in the plasma. And in fact, dust forms. And in fact, this is a problem for the electronics industry, because you don't want to form dust because that will get in the way of the production of semiconductors. But it's something that's interesting in itself from a fundamental point of view. And what we saw was that whereas normally in, let's say, in a plasma with silane or that's used for producing semiconductors, dust forms over a period of minutes. When we injected DMA into a plasma, it wasn't silane, it was an argon plasma, we got dust particles right away. And I'll just see if this this works. And what you saw there in the film was the, let me just go back to that, was these dust particles which were being held in the potential structure within the plasma reactor. Here you've got two bands. When you turn off the plasma power, then your particles, which are illuminated by a laser, that's why you see them as green, they're illuminated by a green laser. You can see them actually dropping down to the electrode on the bottom. So there's your DMA dust, formed dust dropping down. Anyway, so DMA forms negative ions. How do we get electrons? And one of the things I've worked in my career is in combustion, and I know that flames are great sources of ions. Flames produce a lot of electrons, a lot of ions, and so I thought what we could do is, since these cloud seeding processes are using aircraft, that we could in fact inject dimethylamine into the exhaust of the aircraft, which is a very good source of electrons and ionic species. And the idea is to see if we can enhance cloud formation, produce clouds by injecting dimethylamine into aircraft exhausts. And in fact, I have made an application for a patent in the United States to actually look at the catalyzed cloud formation by this process. However, as I say, here's a photograph on the left of one of the typical aircraft that's used for cloud seeding. And on the wing, you see these sort of cylinders with red caps on them. And these are these pyrotechnic flares. And these aircraft fly into clouds and they ignite the flares. The flares burn and emit hygroscopic salts. And this is typical of cloud seeding activities in, for example, the United Arab Emirates are using this extensively. But as I say, during the development of this proposal, I found out about this company in France, rather by accident. And in fact, they, instead of flying aircraft, they fly balloons. And here's a test that was done in a sort of a wind tunnel, where they had a balloon with a pyrotechnic flare attached. And you can see in this film how the flare looks like. So here you see these hygroscopic salts being sprayed out and forming a cloud. And the idea is that these salts will enhance particle formation in the cloud that will lead to rainfall. As you see, it ends up with the balloon. So one of the things is we want to know more about these flares, and in particular, I'm interested to know what is the ion content in the flares. So I talked to Suleiman about this, and we proposed building an apparatus where we would put a flare into a stainless steel chamber using the sorts of chambers that we already have in the CAST laboratory, set off the flares, measure the electron density by, for example, microwave absorption or Langmuir probes, but Langmuir probes are really most effective under vacuum conditions. So in this case, microwave absorption would be the best method of looking at the ionization. And then we can look at the particle size distribution in the cloud by extracting the particles using standard aerosol measurement techniques. And finally, we can inject dimethylamine to see what happens, basically. And so we can study the characteristics of dimethylamine catalysis in a laboratory apparatus that will allow us to make controlled measurements, measurements with controlled humidity measurements. We can work at the reduced pressure typical of the upper atmosphere. And basically, it would be very, very interesting to have such a system that we can study. Goals would be to, as I say, measure the electron density downstream of a pyrotechnic flare to see if that's a good source of electrons for our catalysis. Looking at the particle size distribution, people have already done this for flares, and it's interesting because this turns out to be a strong function of airflow velocity. Characterize the particle size distribution after DMA injection. And also look at different flare compositions. Flares contain magnesium, for example, and with typically potassium perchlorate as an oxidant. Of course, there's not a lot of oxygen up high in the atmosphere, but there's enough to keep things burning. But perchlorate is a very powerful oxidant. And the idea would be ultimately to do an experimental program using balloons from this Cellares company and incorporate the DMA injection into that. And in this way to look at the effectiveness of catalyzed cloud production coupled with seeding. So this is the ultimate goal of this proposed project would be to use to put DMA into the upper atmosphere with the source of electrons and to see if we can generate clouds and to seed clouds and produce rain. by the way, I should mention dimethylamine is a very nasty substance. It has a terrible smell. It's produced by rotting fish. So if you want to think about the smell of dimethylamine, think of rotting fish. It's a natural product. It's a natural derivative of ammonia. And it just happens, but we're going to inject it in very, very small quantities, parts per trillion quantities, perhaps, to generate clouds. So it's not a pollutant that we're putting into an atmosphere. It's a molecule that's already formed in the atmosphere by ammonia. So basically, this is just a slide that shows the setup they have in the with the balloons. Here you have the flare. The flare can be ignited by a microcontroller on this electronics board here. The electronics board in their system measures the acceleration of the balloon as it's going up, measures atmospheric pressure, measures temperature, and that you can time the injection, rather the ignition of the flare and the injection for that matter, exactly when you're in the best possible condition for doing the seeding. So this is basically the approach that we're looking at. So the advantage of this is that it is an all-weather system, and it can be flown under conditions where the aircraft would not want to fly. For example, in the thunderstorms, that balloon will just fly through them, and you'll be able to work over a very much wider set of conditions. Also, you're not subject to air traffic control limitations. Aircraft have to keep within a very strict perimeter when they're flying. They've got to have permission to fly. Also the aircraft has got to be certified for carrying these flares. So this is a very much simpler situation. We're not under air traffic control rules. But there is another thing which I found out about reading more about this, and that is the fact that the low air velocity is very advantageous when you're doing seeding. And this diagram here at the bottom shows the particle size distribution as a function of airspeed. And if you're very low airspeed, you get a particle size distribution there at about a maximum of about 250 nanometers, which is ideal for producing larger species for these cloud condensation nuclei. Whereas when you start to increase the airflow, you suddenly are decreasing the size of the particles. And this is just the kinetics. This is just the fact that the particles don't have time to react with each other. And of course, if you're flying an aircraft, you're flying in these sorts of speed ranges. So actually the aircraft is not necessarily the best system for using it, whereas a balloon that's traveling slowly is rather ideal. And for obtaining hygroscopic particles that are the best for seeding, you want about somewhere between 1 and a few microns in size. And in fact, when you're flying with air speeds typical of aircraft, you're actually creating smaller particles that can actually inhibit raindrop formation. And this is one of the magic secrets of cloud seeding. Cloud seeding is rather controversial because there are many people who say, well, we tried it, it didn't work. Well, why did it not work? Maybe you weren't using it the right way. And so this is why I'm very, very happy about this, doing this using a balloon, where we're actually giving the best kinetic conditions for doing the experiment. I might mention that Celeris, I'm not a member of Celeris, I'm not selling their product, but they're based in the south of France, but they work in Belgium, Poland, Armenia, Ukraine, Romania, Turkey, Spain. And they have a very active program of cloud seeding, and they also incorporate that with radar detection so that they can choose the very best climatic situations, meteorological conditions for beginning the seeding. So anyway, in conclusion, cloud seeding has the potential for enhancing rainfall in desert regions. Remember, in Saudi Arabia, you don't have forests, so you don't have pennines. You don't have widespread agriculture, so you don't have the ammonia. And you don't have the very large installations for creating sulfur dioxide. So you really do not have the actors in place for forming cloud condensation nuclei. And so Saudi Arabia would be the ideal place to study the injection of catalysts. Obviously, we need a good knowledge of the instrumental parameters, how we're going to produce the system, what do these flares do, what are their characteristics. We need some laboratory studies of catalyzed cloud enhancement. We need to characterize the flares. We need to know more about DMA, dimethylamine ion chemistry and physics. And in the laboratory, Atomic and Molecular Physics laboratory at CAST, they have an apparatus that we could use for doing these types of measurements. It's a mass spectrometer apparatus. And we actually, apart from DMA, we can also look at pinene reactions. An ideal apparatus for doing this would be the CAST electrostatic storage ring, which, being electrostatic, it is not limited in mass. And these are very heavy molecules. These are not the sort of molecules you can easily study with other techniques, but you could inject pinene ions into the electrostatic storage ring and study their interaction with other species using, for example, merged beam techniques. And finally, what we really need is a field demonstration of the proposed methods. So anyway, thank you very much for listening. And if you have any questions, I'd be very happy to respond to them. And thank you again for inviting me to talk today.